So, good morning, everybody. I think it's a good time to start.
Here he is.
And so the first speaker is Julian Barbour.
Can I begin by more or less repeating what I said at the end of the dinner? Thanks again. No, not all the spiel about trying to sell my book. Thanks again very, very much to the organizers, Renato, Sandra, and Daniela. It's just been an absolutely fantastic meeting, so thank you very, very much. And I'd like here to take the opportunity to put on record my tremendous gratitude to the Foundational Questions Institute, their directors, Max Tegmark, Anthony Aguirre, their secretary, Kavita, and the backup team of Brendan Foster and Zia Merali, who appeared briefly with that spookiest thing. It's such a public service that Max and Anthony did by setting up that Foundational Questions Institute, so I'm immensely grateful to them. So here's my talk. If I don't get to the end, I'd rather stop and have discussions, but the substance is all in this paper here. So this is very much a might talk. We think we might have stumbled upon the solution to two long-standing problems, so let me plunge straight in. The two problems are, given time reversal symmetric laws, what's the origin of the arrows of time? And the ones we are thinking of at the moment specifically are the growth of entropy, the growth of structure and information in the universe, and the invariable observation of retarded potentials. And the second question, which we think is closely related, is, can we say, do we live in a typical universe? So our key insight is this, that conventional thermodynamic systems are defined, but we suspect that the universe is unconfined. And as far as I can see, looking through the Arrow of Time literature, it reveals very little awareness of the difference between those two cases. I'll say what I mean precisely by confined and unconfined in a moment. But we think that they require very different conceptualization. And in fact, this leads us to identify two entropy-like quantities in a universe. If it's a self-contained universe like a spatially closed universe, or my model will be the an island Newtonian universe. And this leads us to identify two entropy-like quantities. One is scale invariant, we call it entaxy, I'll explain why shortly. And that decreases, and that's the really fundamental one, and that actually enables conventional entropy to come into existence and grow, in our model at least. So here's the summary of the talk. So we have what we hope is a realistic proof of principle model based on the Newtonian n-body model. And our conclusion is, if that model is a true guide, that the second law of thermodynamics must hold in a self-gravitating universe. No special initial condition is required for that to happen. And second, if the law that governs the universe is known, it will have typical solutions. There's a hypothesis there we shall see, but we think it's a plausible one, about which strong predictions can be made. And at the very first approximation, these predictions appear to hold in our universe. So now let me come to the meaning of confined. This is illustrated by the classic example through which the molecular theory of heat was established. Ideal gas in a box. There it is. Now, experimentally, the box permits the controlled supply and extraction of heat, measurement of the pressure, volume, and temperature in equilibrium, and thus going from one equilibrium state to another, determination of entropy increments. And I think nobody would disagree that the second law of entropy and the second law of thermodynamics could never have been discovered without the ability to control the behavior of steam in a cylinder. Now, there's an exact theoretical counterpart of that. Gibbs, in his statistical mechanics, created that discipline for general Hamiltonian systems. He was very proud and keen to make sure it was a general Hamiltonian theory. But he had to make two restrictions. In order to count microstates, of course, in accordance with Boltzmann's famous formula, he had to impose two conceptual boxes. And they both came in the form of bounded measures of different nature. First of all, he says the configuration space must have a bounded measure. And secondly, the momentum space must. And that meant he could not allow forces which would enable the momenta to grow without bound and flood the momentum space. And if you stop and think about it, so that includes there couldn't be one upon r, he says specifically there couldn't be one upon r squared forces, and that means there's no gravity allowed. He doesn't actually mention gravity specifically. But if you stop and think about it, both of those are unnatural. You've got a question, Jörg? Yeah, yes.
Can you please repeat?
Yeah, I'll repeat the question. Yeah, yes. Jörg says that Coulomb forces are fine. Yeah, and of course there's so much mutual compensation as well. But it's the point about gravity, there isn't any cancellation. They just go on building up. Thank you for that comment, yes. But as I say, if you stop and think about it, it's unnatural. A gas wants to expand and everything gravitates. So let's go on. Now, what is the consequences of the confining box? So very important, that desire of the gas to expand freely is thwarted. It leads to equilibrium. The box is isolated, and then we get infinitely many Poincare recurrences. The solutions are qualitatively time reversal symmetric, as you see there. I assure you, most of you are familiar with these sort of diagrams. The thing looks exactly the same in both ways. Poincare had produced his recurrence theorem. He didn't like the molecular theory of heat. I think he was stimulated to get it just to kill it off. Anyway, Boltzmann recognized the recurrence theorem as a severe threat to his statistical interpretation of the second law of thermodynamics, and in a famous letter in Nature in 1895, he said, "I assume the universe is and rests forever in thermal equilibrium." And then it's only near the deep entropy dips here that where visible motion and life exist. And then the direction towards the more improbable state will be called the past. So this is a one past, two futures interpretation. The intelligent beings are here, and they say the direction of time is from order to disorder and heat death. And of course that caused some people to commit suicide in the 19th century. I'm not referring to Boltzmann, it's to other people. It was terrible. And I think it's actually behind, if Nicolas Guizin promised to watch me on the online of this talk, I think this may be behind why he was so concerned about what's going on in dynamics. But let's just summarize. Boltzmann says the second law is due to a huge fluctuation in our remote past. Today that has been transformed into, most people say, the Big Bang must have had an exceptionally low entropy so that it can have gone on increasing forever. Now I want to introduce you to something quite different, which we call unconfined Janus point systems. So this is where the gas can expand freely. And in them, every solution splits into two at a unique Janus point, which is sitting in here in the middle of these Janus heads. And either side of this point here, there is a solution. Half of the solution goes that way and the other half goes that way, and effectively each half is strongly time asymmetric. So we actually have two arrows of time in this situation too. They go from that central point in opposite directions. So just as with Boltzmann, but we'll see with a very different origin, each solution has one past and two futures. And any intelligent observers must be one side or the other, and they must find an arrow of time. And moreover, all solutions are similar. Every single solution has this structure. So it's a very characteristic situation. So the simplest example of this is pure inertial motion. You have here the equation of motion, here it is, the position vectors at time t, they're the initial positions plus the increments that come from the constant velocities. And these grow with time, so with time they completely dominate what the value of that is. This becomes ever less significant. Now, this means that the moment of inertia, here's the center of mass moment of inertia, there's the expression for it, it has just one minimum. And that's the Janus point. Here it is in this diagram here. What happens here is that the particles which at this Janus point have the fastest velocities, they keep on getting further away from those that have lesser velocity. So as you go on, the system inevitably tends to Hubble-type expansion. And you find that any two particles you look at are separating from each other. The rate of separation is proportional to their separation. So, and what you find in any solution, if you look at the state here, you find that the positions and the velocities and the momenta look completely uncorrelated, but as you go out here, they get very highly correlated in both directions there. And intuitively, you always read in books that entropy is a measure of, it's how order is transformed into disorder. And if you stop and think about this, this is really the exact opposite of that, because this is a very highly specialized motion. Now, in the literature, you will find a discussion of half of these solutions. It's when you speak about a gas which is confined and then you suddenly let it escape. And they talk about that free expansion there. And in fact, remarkably, Tolman in 1934, in a very influential book, said that that system is corresponding to maximum of the entropy. I think that's very questionable, so let's think about that. Now, the second example I'm going to give you is dissipationless waves of compact support. So the story which you often get is somebody throws a stone into a pond, there's a disturbed motion where it goes in, and then with time, beautiful outgoing waves are formed. So let me forget about putting the stone in and just suppose that I am given a region of disturbance of compact support. So I'll get that thing there. Now, the underlying equation is time reversal symmetric, so you just flip the arrow to reverse the direction of time, and you have what looks like very incredibly finely tuned waves, very large radius out there, converging on a much smaller region where they become disturbed. Now, of that situation, in a famous debate with Ritz, Einstein in 1909 said, advanced waves are not observed because the initial conditions are statistically improbable. But now just look at the complete solution. Every solution has this form. It's nothing whatever to do with any initial condition. It's a complete mistake to ask what are the initial conditions. Look at the solutions. And this suggests to us that we live in a Janus-type universe in which retarded potentials are attractors in both regions. So to answer Einstein, I'll echo President Kennedy. Ask not what atypical initial conditions can do for solutions. Ask what typical solutions look like. That's where you'll find the answers. So now, so the question is the universe confined or unconfined? If it's confined, then you have this awful nightmare of eternal recurrence and this brief existence where we're conscious and things like that, and we're doomed to go into heat death there. And it occurs infinitely often, and it looks exactly the same both ways. And there's a suitably gloomy Poincaré presiding over these things. Now we go to the Janus systems. It's completely different. There's just one triplet of things, and instead of order being in the middle and disorder on the other side, you have disorder in the middle and order on the outside. So in the recurrence situation, the time direction is statistical in origin, and it goes from order to chaos. In the Janus situation, the time direction is dynamical in origin, and it goes from chaos to order. So now I go on to the a much more realistic one, which is, things are much more interesting when you get gravity into the situation. So our model is what we call the relational n-body problem. Now we want to consider the universe as an intrinsic entity. We don't want anything in that universe to be affected by anything which is outside it. And Newton introduced things extrinsic to the universe, really, when he introduced absolute space and time. Absolute time allows you to change the energy and have many solutions with different energies. And absolute space introduces absolute orientation, allows the system to have angular momentum, and that distinguishes a direction. And that, for the whole universe, is just frankly implausible. So we get the model we want by just saying we take Newtonian gravity as it is, but insist we will only look at the solutions for which the center of mass energy is zero and the angular momentum is zero. And that's an exceedingly interesting system. It's scale invariant because if these quantities are zero, if they have any non-vanishing value, they will change with your units. But if they're zero, zero remains zero, whatever units you have. So that's our model. Yeah, yes? The question is, who decides what's the absolute zero of energy? We're assuming that the Newton potential goes to zero when the system has infinite expansion. Thank you for the question. Everybody got the question all right, did they? Good. Right. So now the joy about all of this is that pretty well all of the key points are explained by the Newtonian three-body problem with zero energy and zero angular momentum. So everything that's really comes out of this one thing. And it's very appropriate. The three-body problem is a really great problem. It's been around since it gave Newton headaches, and it's the first non-trivial problem in dynamics. And let me say, virtually nobody ever learns anything about it pretty well. Very few people know anything about it. Now, actually, the solutions for this case have their qualitative nature, except for a set of measure zero, which are not much different anyway, and I'll ignore them. These have been known essentially for 100 years, since a Finnish mathematician, Sundman, established their nature. It's called hyperbolic elliptic escape. So taking one time direction, you have a single inertial particle going in one direction and approaching it in the opposite direction. This is in the center of mass frame. We have a well-formed Kepler pair out here. As they get closer to each other, they disturb each other's motion. There's a period of non-trivial three-body interaction, which may or may not lead to a swapping of pairs. In this case, there is a swapping of pairs. One inertial particle goes off there, and down here a new Kepler pair forms. And you can read that conventionally. The way you read it is you can read it that way with the arrows going like that, or you can read it in the opposite direction. Coming in the opposite direction, it looks qualitatively the same, but the details are different. So that's every single solution is like that. And in fact, this solution too has a Janus point, because at that region of strong three-body interaction, non-trivial three-body interaction, that's where the moment of inertia is minimal. So now that's the normal interpretation. Now there's a Boltzmann type interpretation of this, which gives one past and two futures. Now in this one, we say that each diagonal is a history that begins at that Janus point there. So here's the beginning for this diagonal. Oh, and note that I've reversed the arrows. In both cases, on both diagonals, I've got the arrows pointing away from the Janus point. So here's the sort of, as far as any observers out here might be concerned, and if you've got a lot of particles, then it's realistic to say there are observers. So from this chaos here, bit by bit, two particles separate out, and they go off and form a beautiful Kepler pair going down this way, and the other particle goes off there. So you have the qualitative symmetry of the histories, because the two diagonals are not identical, but it matches the exact symmetry of the equation. And in fact, actually, you can use the Kepler pair as both a rod and a clock. And with respect to it, it tells you how far you are from this Janus point, which tentatively I'll call the Big Bang. So, and using that, you can measure time from that Big Bang, and you can also use the rod and the clock to confirm that this guy is moving off in pure inertial motion. And in each history, the universe expands as measured by the length of the major axis of the Kepler pair. It can see that this guy is moving away and the universe is expanding, and it breaks up into branch systems. These are just the, so to speak, two clusters. Whoops. Very simple ones of the single particle and the two-body one. The notion of branch systems was introduced, the terminology, by Reichenbach, and it's a nice account of it in Paul Davis's book of 1974. Gravity creates structure out of chaos in this picture, in every solution, and for internal observers, the only sensible direction for the choice of time is fixed by the growth of structure, information, and records. And by information and records, I mean that the orbital elements, they stabilize ever better to ever more digital positions. And that just goes on getting sharper and sharper for eternity. Let's go on to the next slide. Now, next thing to note is that the universe in its totality is described by a dynamical law which has a very different nature from the dynamical law which describes the subsystems, but it never describes the subsystems with perfect accuracy. It's only an asymptotic state of affairs. So the universe as a whole is described by a gauge theory, and you see that because of these constraints there. That's the very characteristic signature of a gauge theory. And so the law of the whole universe is governed by Noether's theorem part 2, but the branch systems asymptote to states which have conserved non-vanishing energy, momentum, and angular momentum. And that corresponds to Noether's theorem part 1. Jörg? The question he confessed his ignorance. Dare I say, in slight difference from earlier, that was a bit naughty. Noether's theorem has two parts. Noether proved this famous theorem in 1919. It's absolutely crucial. It was a long time before it got translated into English, so a lot of people don't know about it. She says, whenever there's a variational problem, and then she says, when the action is invariant under a Lie group with a finite, that depends on finite parameters, then you have conserved quantities, and that's Noether's theorem part 1. If the Lie group depends on arbitrary functions, then you have, as Dirac much later showed, then you have these constraints. You have Dirac's beautiful theory of constrained Hamiltonian systems, and you've got a quite different situation. So those are the two parts of Noether's theorem. But thank you very much for the question, because I'm sure a lot of other people weren't aware of it. Thank you. But this suggests to us that you should treat these two systems very differently, and in particular, that the statistical mechanics for them may be very, very different. And this is why, for the n-body universe, at least in our toy model, we introduce this entropy-like quantity entaxi. I'll put you out of your misery. It's a coining from the Greek from Flavio Mercati, who like all well-educated Italians, is a great scholar and knows it's Greek and Latin. Taxis is the Greek word for order, and entaxi is towards order. So it's a measure of how gravity can create order out of chaos. And this, as we shall see, we can quantitatively measure how it decreases in both directions, outgoing in this branch or this branch, as you get away from the Janus point. And then we will be able to show that these branch systems will be born with a Boltzmann entropy that increases in both directions away from J. So we are led to two quite distinct properties. This entaxi is going to be scale invariant. The Boltzmann entropy will be dimensionful, and they behave in opposite ways. And it's the decrease of the entaxi which forces the emergence of the branch systems and leads to the Boltzmann entropy increasing. So next one. So now we want to set up a statistical mechanics for universes, and we're going to have counterparts of Gibbs's conditions. So any entropy-like quantity must be a count of microstates, and it must be in a phase space region of bounded measure defined by a state function. Now, in Gibbs, if you take the microcanonical ensemble, your state function is the energy, and your macro state is then the volume of phase space occupied by those states that have that given energy, and your entropy is just the volume of that thing there. That's the count of microstates. And let me emphasize that mere monotonic increase of some quantity, that makes it a Lyapunov variable, but it's not. It's got to be a count of microstates to be called an entropy. Now, for our whole universe, we're going to insist that state functions and measures must be scale invariant. Now, ideally, we want state functions to reflect fundamental properties of the universe, just like the energy does in statistical mechanics. One of the prime questions of interest is how does the entropy change when the energy is changed? So our aim is to set up a theory of the typicality of universes. We're following a paper of Gibbons, Hawking and Stewart from 1986, but we've got significant differences. And the really significant difference is that at least in the n-body problem, we will have bounded measures, but they had infinite measures, which means that actually any statistical applications you tried to draw from the theory failed. So
You refer to typicality and natural measure a lot, but obviously this is the crux of the matter. I mean, you need to define typicality. You need to postulate a measure.
yes, exactly.
And justifying what measure to use is, in a sense, the
Absolutely.
key problem. Of
Yes.
mechanics.
Did everybody hear the thing there? Yeah. To make claims about typicality, we have to define a measure. We have to justify the measure. Now, we think there is a very simple choice for the measure, but it remains a hypothesis. So, and that has to be confirmed a posteriori. But the theory will lead us, I think, very naturally to what we should choose. Thank you very much for the thing there. Now, the great. So our key concept. Is our scale invariant concept is shape space. Now, the Newtonian n-body configuration space has 3 n degrees of freedom, and of these, translations and rotations are 6, and they don't play any role in our relational model. They've gone. Now, absolutely crucial is that there is just one scale degree of freedom. That's represented by the square root of the moment of inertia, if you want to give it the dimensions length. And that's the sole scale degree of freedom. And all the other degrees of freedom are shape degrees of freedom. And our whole story really comes from separating out the effect of that scale degree of freedom from the shape degrees of freedom. So this is all part of our shape dynamics, as we call it. So those shape degrees of freedom and the mass ratios, they define shape space, and it's the quotient of the Newtonian configuration space with respect to the similarity group of Euclidean translations, rotations, and dilatations. And shape space is compact with bounded measure. So when you take out scale, the universe comes with its own box. So that deals with Gibbs's condition without anything artificial. And the joy about the 3-body problem, if n is 3, shape space is the space of triangle shapes, and 2 angles, internal angles, fix the triangle shape. So that means that you can represent shape space as a shaped sphere. Here it is. The color coding I'll explain in a moment. So basically, points at equal longitude and opposite latitude correspond to mirror images. The zero angular momentum 3-body problem is planar, so mirror images are distinct from the other ones. The equator corresponds to the collinear configurations, and equilateral triangles are at the poles. And I'll come on to what those things mean in a moment. So now, if you take any Newtonian theory with energy and angular momentum, you can always project it to shape space, and you do not lose any objective information that can be determined from within the universe. So that's a key thing. Now, so what they become in shape space is undirected, unparametrized curves. So if you're going to, you can get back to the Newtonian representation. It's not all that easy, but you must be able to because you haven't lost any objective information. So now, if these curves were geodesic, a point and a direction would fix a solution. And this very strict Laplacian determinism fails because of the angular momentum, which has three components. The absolute metric of time allows different values of the energy, and the absolute scale allows the moment of inertia to change. And that means that the Cauchy data in shape space are a shape, a direction, and 5 more numbers. Now, our relational conditions enforce those conditions which kills 4 of those 5 quantities, but you cannot kill what happens due to the scale. That's absolutely, and that's going to be the beginning and end of the story. So the Cauchy data in shape space are not a shape and a direction, but a shape and a tangent vector. There's just one more datum that comes into the story. And that it's one single Hamiltonian degree of freedom, and it's absolutely crucial. It's architectonic, as I'll now show. So there is a very fundamental relation known as the Lagrange-Jacobi relation, which you probably will know as the virial relation. Lagrange discovered it for the three-body problem in 1772. So pretty well our entire work with the Janus point relies on the first qualitative discovery made in dynamics by Lagrange in 1772, 243 years old. So if you have a homogeneous potential, which you do in the Newton case, you multiply all the arguments of the potential by a common factor. It will give you back the potential multiplied by that factor to the power k, which is the degree of homogeneity. And if that's the case, straightforward application of Newton's second law leads to this virial or Lagrange-Jacobi relation, which says that half the second time derivative of the moment of inertia is equal to the energy plus this expression multiplying the potential, and k is the degree of homogeneity. It then follows that if the energy is non-negative, because the Newton potential is negative definite and k is -1, that immediately tells you that the second derivative of the moment of inertia is positive definite. That immediately means that the moment of inertia is U-shaped upwards, and its first time derivative, which we call the dilatational momentum, it's the exact analog of angular momentum, but it's a scalar product. It has the same dimensions. It is monotonic and vanishes once, as you see in the figure. And the wiggly curve I'll explain later. Now, it's architectonic, this thing, because this d, the dilatational momentum, it's a Lyapunov variable. So there are no periodic solutions. You can deduce that straight away if the energy is non-negative. And there are no Poincaré recurrences. So we can put to bed that nightmare. So at the Janus point here, it's marvelous because at this point, a point and a direction do determine the solution. The reason why in the previous slide you had that tangent vector is that at any other point, the kinetic energy has 2 components, the shape kinetic energy and the kinetic energy of overall expansion. But at that one unique Janus point, there is no kinetic energy and overall expansion. So that is one unique point at which you can specify solution determining data in scale invariant form. So at this midpoint, solution that we get that. This data that determines every single solution, it's scale invariant, non-redundant. It's the absolute minimum data that you need, and it's unbiased. I'll come to the significance of the unbiased. So let's go on to the next slide there. So the next thing I want to talk about before getting on to more nitty-gritty thing is the fact that there are attractors in shape space. In the Newtonian phase space, the Liouville measure is conserved. But if the scale part expands, that must mean that the shape part decreases. And therefore, what I'm showing you here on the shape sphere is, so to speak, a Gibbs ensemble of 22-dimensional inertial motions. So they all start with the same velocity, but they have initial positions reflected in their different position on the shape sphere. And you can evolve them forwards or in either time direction, and they all converge on a unique point. So you see this very powerful attractor at work already in inertial motion. And it's much more interesting, as we'll see when we get on to gravity in a moment. So now, before I do that, I want to introduce something to measure what gravity does to matter. Now, everybody is familiar with people saying that gravity is in some senses anti-thermodynamic in that it can transform a uniform distribution of matter into a clumped one. So now we want to have some scale invariant measure of this clustering, and it's got to be scale invariant to be objective. What does it mean to say the universe is expanding? Well, that the typical galactic diameters divided by the typical intergalactic separations is tending to zero. So if we're going to have some quantity which is scale invariant and measures that clustering, we'll want to take the ratio of two lengths. And luckily, mathematics gives us two fundamental lengths which are beautiful. Jonathan, you want to ask a question?
If you're talking about clustering, why would it not be better to look at clustering in phase space? Because I mean, things may cluster in position, but gather more.
The question is, if we want to talk about clustering, shouldn't we be looking at it in phase space? There's a rather interesting reason, which I'm coming to, why we don't have to worry about that. The much more interesting thing turns out to be the clustering in configurations in the shape space. I'll explain it. It's to do with dynamical similarity. So first of all, we want to get this quantity here. Mathematics gives us two mass-weighted quantities which are ideally suited. One is the root mean square length, and here it is. That's an alternative. In fact, that's the definition of it, where RAB is the separation between the particles. It's actually an alternative expression for the center of mass, the square root of the center of mass moment of inertia divided by the total mass there. So that's very close. And this quantity is dominated by the largest separations in the system. The other one is the mean harmonic length. There it is. And it's the inverse of the Newton potential divided, in this case, by the square of the total mass. So we just define the shape complexity as the ratio of those two quantities, which is actually, because there's a -1 here, it's actually the Newton potential effectively multiplied by the root mean square length. And this is a very sensitive measure of clustering, because the minute particles start to huddle together, the Newton potential goes rocketing up. So it grows there. But when those particles get closer together, in a system with a lot of particles, it has virtually no effect on the root mean square length. That barely changes. So it's a very sensitive measure of clustering. And this is actually, now I can explain what these contour lines are, the color coding. It's just plot of this quantity here. This is a pure number. It has its absolute minimum at the equilateral triangle. By the way, in the three-body problem, for any values of the mass which Lagrange discovered, these are the contours, and it goes to infinitely large values at what we call needles. That's where two particles are much closer to each other than the third. And it goes to infinity not because the Newton potential, because two particles got together and the Newton potential is going to infinity. It's going to infinity because that ratio is going to infinity. So we're sticking to our principles. So let's go on. Now, there's a very interesting thing about this. It is not only a very sensitive measure of clustering, it actually turns out to be what n-body people call the shape potential. Because what does the Newton potential do? It generates forces that do two things. First, it pulls all the particles towards the common center of mass, and that's unobservable in shape space. It does not change the shape of the system. But much more fundamentally, it changes the shape of the system, and that's observable for internal observers. So now, the multiplication of the Newton potential by the square root of the moment of inertia kills those unobservable forces, and it gives, and if you take minus that quantity, it is actually the potential that changes the shape of the universe. And I don't think this fact has been noticed. It looks to, you can interpret this as saying Newtonian gravity has been designed to create clustering. It's sitting there right at the heart of the mathematics of Newtonian theory. So now let's have a look at the effect of the attractors in Newtonian gravity. They're much more powerful now in this case because here's that solution that we saw before, but it's now plotted as curves on the shape sphere. There's the Janus point at the back there. The two halves are time asymmetric. Effectively, when you give a Hamiltonian description, it turns out to be minus the logarithm acts as the shape potential. But basically, you have something makes the dynamics look dissipative. So the attractors plus gravity together means that you have those isolated clusters forming. That's why you get that Kepler pair and the single particle. And they cannot, wherever you start that system at its Janus point, there's only 3 places where it can finish up on the shape sphere. It's got to be at one of these things. That's the deep potential wells, if you interpret it as the shape potential, or the peak of the complexity. Jonathan, a question.
So maybe now I can ask the question again. So you're interpreting this as emergent second laws because you're reducing entropy.
Well, not that. You're saying. He's anticipating the talk in saying I'm interpreting this as the emergence of the second law. Not quite. Let's just wait a minute before we say that, if I may. What I want to say, by the way, the momentum is not so interesting because what the momenta do, they go into limit cycles rather than to converge on a point. But that's a relatively minor detail. But what I'm saying is the fact that you get isolated clusters with lots of particles in, if you've got a really system with millions of particles, that's what's going to make it possible for the second law to emerge in the clusters. Okay, so I jumped too much there. No, that's there. Now there's that solution again. Now I can tell you what this curve is. This is now the only thing that is directly observable in the system. This is how that complexity function varies. And you see here, it's completely it splits absolutely clearly in 2 at the Janus point. The complexity is going up. These fluctuations come about because the Kepler pairs seem typically to form with a relatively large eccentricity, so the separations between the particles are fluctuating rather strongly, and that causes those fluctuations. But that complexity rises unambiguously between linearly rising bounds, and that's an arrow of time. That was actually what it was. That insight that is behind our paper in PRL nearly a year ago. So that's the story. That's the meaning of the complexity. So now, if you have a 1,000-body simulation, we did. Can I just finish this slide and then I'll take your question, Jörg? If you have 1,000 particles, which somebody kindly did a simulation for us, the clusters that form mostly transiently, actually near the start, their phases are not synchronized, so the curve gets smoothed out. So there you see again, absolutely clear the Janus point and this very marked time asymmetric behavior on either side. And this is a purely artistic representation. If you could sort of see only the shapes, at the Janus point, basically it's like a swarm of rather uniform swarm of bees with all of the bees going in random directions. But as you go out on both sides, you get structure forming, and you asymptote essentially to a Hubble-type expansion. So that's it. Your question, Jörg.
So, I mean, this is all very nice, but it has not much to do with our universe, because in our universe there are other forces as well that, for example, enable us to measure scale.
Yeah, the question was, he says it's nice, but what is really the connection with our universe? Because there are other forces that enable us to measure scale. Now, perhaps we can leave that one point to the end. All I want to emphasize again is that this is a proof of principle. It's a very simple model which enables you to do it. And in fact, actually, your question is to anticipate any later answer. It's related to the role of the Higgs boson, I suspect, bringing in a mass scale. But anyway, let me go on to the next slide. So let me just say how everything depends upon these midpoints. If you read anything on the arrow of time and the second law of thermodynamics, people say it must be an initial condition. Nowhere in any of that literature have I seen anyone ask, what do I actually mean by an initial state, and where am I applying it, and things like that? Or is it an issue about applying, saying I've imposed an initial condition? So the key thing here is that each solution has its unique Janus point. As I've said, at that Janus point, a shape and a direction do determine a solution. So it's scale, and that you can set scale invariant. Now it's unbiased, because at the Janus point, that's the one position in the entire solution where those attractors have not set to work and are strongly influencing the solution. So those attractors are powerfully at work. It's just at the Janus point where they're having no effect. And it's non-redundant data. You can't get down to specifying anything with less than that. And it's the minimal encoding of all the objective information which is conserved by the evolution. Now, just technically, the cotangent bundle of shape space is shape phase space, but the vectors in that thing have direction and magnitude, so that has an infinite measure because of those magnitudes. Now I'm going to show that. Did I jump a slide? Yes, I have. Sorry, wait a minute. I know I've done chaos. Wait a minute. How do I go back to full screen? Sorry. Let me go back to. I jumped a slide. Yes, sorry, I jumped a slide. Thank you. This is the other important thing, is dynamical similarity. If the potential is homogeneous, then this scaling like this, multiply all the position vectors by a constant, and then multiply the time by that same constant, but to a power which depends upon k, that maps solutions to geometrically similar solutions, and the case k equals -1 generalizes Kepler's third law. Now, note this is not an Noether symmetry because it changes the action. So it's a perfectly bona fide symmetry, but it changes the action. And our thing relies crucially on the fact of these two symmetries that we have at play. And this means that if you're considering the whole universe, solutions with momenta of the same direction, but different magnitudes, they are identical in shape space. You cannot tell them apart if you're a godlike observer looking at the whole universe. So you just can't tell what's there. And so this means that Gibbs's exclusion of 1 upon r squared potentials is unnecessary if we're considering the whole universe. So and moreover, we've got a compact shape space, so both of Gibbs's boxes for confined systems arise naturally for the physical observables in the unconfined n-body universe. So I should have put that in before, sorry. And that actually resolves your question, Jonathan, about worrying about the momenta. Well, to some extent it will do that.
Are you saying there's also a minimum of Janus point in phase space?
No, you need the complete curve either in shapes. You can get the complete Newtonians. You can find the Janus point from the curve either in shape phase space or from there. No, sorry, we're getting. Let's leave that for a moment. So, sorry, no, I've got to go back to there. So, so the elements of the cotangent bundle, they have direction and magnitude. But as I've argued and shown, for the whole universe, that magnitude is irrelevant. So that actually, when you take out the magnitudes in the cotangent bundle, you get what's called the projectivized cotangent bundle. We can call that the Janus manifold, and every single point of that fixes a distinct solution. So now this is an odd-dimensional thing. It's contact geometry, and you can read about it in Arnold's mechanics. But the key point is, every single point of the Janus manifold maps the points map 1-to-1 onto the solution space. So we've got total control over the solution space in terms of scale invariant information. Now comes a key assumption. There is a symplectic measure induced on the cotangent bundle, but it's infinite. That's again because of those momentum magnitudes. So actually we're going to use a measure which is metric. Now, on the Newtonian configuration space, you can find a nice scale invariant metric. It's a very obvious one. You take the standard kinetic metric and you divide it by the square root of, by the moment of inertia. That gives you something which is scale invariant, and it's unbiased in shape space because this doesn't do anything to the shapes. And then there's a procedure called Riemannian quotienting, which enables you to, using that as a starting point, to induce a distinguished metric on shape space. So we've got a metric on shape space, and moreover, at any shape, that metric is going to make it possible to attribute a norm to the shape momenta and actually get the shape momenta under control as well. So we've got, for shape space and the space of relative shape momenta, we have bounded measures without those Gibbs-type restrictions. So now I come to the key thing is that we can now define typicality of solutions. So what we say, so we're going to use the shape momentum, the shape complexity and its momentum analog. I won't go into details about that, and to be honest, there are possibly choices of there, but basically there certainly will be something there, and it will be a hypothesis which will ultimately have to be checked. But we're going to use those as state functions. But I'm just going to talk about the shapes at this stage here. So every point on here is a shape microstate. It's a triangle, a shape of a triangle. And that's an area, this is a macro state on the shape space between these two contours there. So, but in principle, in fact, actually we're talking about, I've got slight model here because I'm getting the momentum in as well. But let's say we'll take the momentum as well. So all the microstates on a given level surface defined by that defines a macro state with a certain volume, which is induced by the shape metric. And that, then we can take the logarithm of that, and we call that the entaxy of a solution that has those complexities at its Janus point. That's crucial. 10 minutes, thanks. I think I can just about finish. So this is a scale invariant entropy-like quantity, and it tells us how likely it is for a universe to have a given shape and a given shape space direction at its Janus point. And that is effective, that's the effective initial data for observers who live on either side of the Janus point. That is their, so to speak, their Big Bang, their initial starting point. So now we come to, this is the hypothesis, we assume we know the law of the universe. Can we predict what typical universes will be like? And in circumstances like this, if it's Laplace's principle of indifference, if a certain number of outcomes are possible, but nothing else is known, give equal probability to each. And of course, this needs the measure. So our chosen measure, this combination of Laplace and the measure will have to be tested a posteriori. And it is, I shall show you, I've just about got time, to verify the principle and the chosen measure a posteriori if they make multiple predictions. If we've got an n-body system, it can make multiple predictions. So we're following basically Gibbons, Hawking, and Stewart, but now we've got bounded measure and, as I say, total control of the solution space. We follow Laplace. We give equal probability to equal bounded measures, regions. So the probability of occurrence of a universe is proportional to its entaxy at its Janus point. So there's its initial shape and there's its initial direction. It's sitting there. We've got the shape complexity and we've got the corresponding momentum one as well. And that tells you how likely that solution is to be realized. So that's it there. And in fact, if we're just talking about the shapes, this is a faithful representation of that metric, and you can just read it off there. It's obvious that those needles, where two particles are very close to each other compared with the third, will have a very low probability of occurring. It'll be much more likely to be somewhere in that region there. So we just go on. Now, for the three-body problem, that's already quite interesting, because actually, I'm just talking about the shapes now. If you go out to 1.5 times the minimum, this is the current complexity and that's its minimum value. If you go out to 1.5 times the minimum value, you've already encompassed about half of shape space. But if you increase the number of particles, then you get a very pronounced peaking. So at 100, you only have to go to barely 1.1 times the minimum to have encompassed virtually the whole of shape space. Now, there are some caveats about these curves, which we can perhaps discuss in the things, but at least to us, this suggests that typical universes will be very uniform at the Janus point. And that's what I mean by saying that, in a second, that in the very first step, we begin to be recovering something that looks like our universe, because the Big Bang does seem to have been very uniform. Question, yes?
So I think I missed one point. So where are your probabilities coming from? So
we have a measure on shape space. Oh, sorry, where are our probabilities coming from? We have a measure on shape space, and we have, we're applying Laplace's principle. So we're saying anything that is, I went just too fast. So I take all of the shapes which are here in this region between two contours, and I say that the probability of finding things within that area is proportional to that area there.
So maybe you should refer, so what motivates your measure in the first place?
Simplicity. I would say any other choice would probably violate the principle of sufficient region. We're still thinking hard about the shape momenta part, the momenta part of it, but there will be something out there which will have to be verified a posteriori. Jörg again.
But who is doing the experiment with all these different universes?
Ah.
To guarantee to us that we are living in a typical one.
Right. The question is, who is doing all these observations to guarantee we're living in a typical one? We are, because we are going to make observations. If our theory is on the right lines, it will make strong predictions about what we will actually observe. And therefore, by looking, it will say, if we're in a typical universe, you will see these things. And I'll show it actually in the next slide, because I'm virtually at the end now. That's that one. So in fact, in the three-body problem, there are two asymptotic. Is this for the leaving 10 minutes or the end of the hour? It's the end of the hour, isn't it? Oh, dear. Yeah, okay, all right. I am literally at the end now. Well, there's one more slide after this. So in the asymptotic limit, there are two scale-invariant quantities which emerge. One is the eccentricity of the scalar pair, and the other is the angle between its major axis and the direction to the escaping pair. So McCarthy did numerical simulations where either you started off with the complexity less than 1.5 times its maximum or greater than. And then he just found out he plotted a histogram for this quantity here. And you see the histograms are very different. So this is clearly, it's making a prediction. So it is in principle. Now, at the minute you have many more particles, you're going to get many more quantities that you can predict and check by observations within the universe. So in principle, I think it's okay. Now, finally, the typicality of states as opposed to functions, we define a current entaxy. That's the current entaxy of a solution. As we define the current entaxy as a solution it would have if it were at its Janus point. We take its shape and direction, and that actually decreases. So that's why that decreases. That's because of these attractors that are there. And this shows that the probability for a universe to be created randomly in its current state is always decreasing from the maximum probability, very near but exactly at the most uniform state. So that's an exact inversion of the Boltzmann picture. And the second law, really, the attractors force these clusters to form. They will form, each cluster has a negative energy, it's metastably bound. Once again, nature gives us what Gibbs needed by imposing something, because they're basically bound. These clusters are branch systems. They avoid the time reversal and recurrence objections to Boltzmann's H theorem, because they're created in the past of internal observers. And so then you find that a second law holds. Coarse-grained descriptions assign an increasing Boltzmann entropy to the subsystems. There's papers about that. So this pervasive time asymmetry either side of the Janus point ensures all arrows of time point everywhere and everywhere and every when for all internal observers. And let me emphasize again, this is only a proof of principle. So thank you very much. We've got about 5 minutes perhaps for discussion.
Very interesting, thank you. Main question is about the expression of this in general relativity, where there isn't, I don't know anyway how to formulate the virial theorem in this theory, and so I wonder in particular how the argument would look that there exists a Janus point if one isn't able to appeal to this, or if you think there's an analog that one would appeal to. And I guess I also was just worried about the simple example of a potential that is zero. So I'm looking at free particles, and there, I seem to understand the argument that if I have a homogeneous potential like that there should exist a unique Janus point. But if I've just got a bunch of particles all moving in a line in one direction, there doesn't seem to be a Janus point. So I was a little confused about that example.
But the potential, and for the second part of the question, for inertial motion, the potential is zero, so it's homogeneous as well. So it's just covered by the same thing there. No, it is a Janus one. That was my very first slide illustrating the central thing there. No, it's absolutely there. It's the simplest one. The very simplest thing that you can consider. The question about general. First of all, this, if it's going to work in a distinguished foliation. In shape dynamics, there is definitely a mathematically distinguished foliation by surfaces of constant mean curvature. Now, even Roger Penrose, who's the most committed relativist I know, says if he's going to talk about entropy of the universe, he's got to introduce a distinguished frame of reference, and he does that by appealing to the Friedman-Robertson-Walker distinct things. Schifrin and Wall, who attacked the Gibbons-Hawking paper, they talk about constant mean curvature surfaces. There is definitely a Janus point in expanding and Big Bang being crunch ones. That's at maximum expansion, but we want it to be at the Big Bang, and there is where a lot of work has to be done.
You said you get conventional thermodynamics in each cluster, in a sense. But what happens if you consider interactions between many clusters, which are still a tiny fraction of the whole universe? Would you get usual thermodynamics about that as well?
I think you probably would if they're interacting with each other. I mean, a key thing in all of this is virtually all of the discussion about thermodynamics, system mechanics, assumes that the systems are exactly Hamiltonian. But actually, these branch systems never become perfectly Hamiltonian. Yeah, I think Jörg wants. Do you want to come in on that point, Jörg? Oh, hang on a minute for the mic, if you would.
But there was a question back.
Oh.
So, it could happen that two or more clusters form, so that one cluster has a negative total energy and the other one has a positive energy. But if you add the energies up, you have your zero energy condition, which, of course, I didn't understand anyway. But now the clusters will separate, and the cluster with the negative energy has absolutely no thermodynamic behavior. Systems of Newtonian particles that have an energy that can be, negative do not behave thermodynamically.
They still have there's a lot of literature in astrophysics on this. A lot of it is around globular clusters. And you can define, although you don't have the conditions for what is it? What's the opposite of intensive? Extensive. You lose the extensivity, but you can define an increasing entropy, and there's a thing called the gravothermal catastrophe, which was discovered by the Russian Antonov in 1962. The entropy, in principle, the entropy will go on growing forever. In the Newtonian gravity, the conjecture is that it finishes up with a very tightly bound Kepler pair and other particles escaped. In general relativity, the story is it ends with the gravitational collapse. But I think, yeah.
Yes, I think you are somewhat addressing the observer problem. It seems to me that what you are stating is any universe that can be described on the basis of observations necessarily evolves to bring about the observers who do the observations?
That of course now there we would have to have quantum mechanics. We would have to understand light. As I said, this is a proof of principle model, and at some stage we're introducing godlike observers at this stage. But at least as a mathematical thing, it's out there, I believe, which is indisputable. Jonathan, I think you were next, were you? Yeah, you've got the mic.
Yeah, I was just wondering if you do it in full GR, you'll have gravitational radiation. So although these systems can lose in full GR, they can lose energy. They'll emit it in gravitational radiation, which you ought to, I guess, include in the.
Well, I think this is going to. Yeah. I think this is just going to lead to the. I think our hope is that this will lead to why we invariably observe retarded waves. I mean, we know the binary pulsars are giving off gravitational waves exactly in that way. I think it's just all part of this pervasive arrow of time. It's just built into the dynamics. Once you allow this universe to expand, it's just that one extra Hamiltonian degree of freedom. The whole of the structure in the universe, I suspect, is due to the combination of gravity allowing or keeping that expansion in, and I think this is the answer to Nicolas Jassin's worry about that. His thinking is too much dominated by confined systems. All of structure in Newtonian theory comes from that one fact. If you can change the potential, and then you don't get structure formation. You get into Poincare type things. I think the choice is either we go for Poincare or we go for Janus type things. And if the Janus, then we're alive. That coin, by the way, I showed, when you look it up on Google, underneath it says, "The God of Beginnings."
So thank you very much for this very inspiring talk. Let's thank the speaker again.
Okay.